In this video, we're going to look at one of the three problems selected from the April 2017 exam by you and your colleagues, looking at the section H from the 2017 April exam on surfaces. The entire question is based on this formula here, or this function here, z equals x minus root y, on the region that's shown in the diagram here. 0 to 4 for x, and 0 to 4 for y. We're asked to draw the contours to start with, and we're given 0 as a starting point, so let's dive right into that. Z is what we're setting, and that's going to give us a relationship between x and y. Now this already defines a graph. The problem is, looking at that, most of us don't know how to sketch it. So we rewrite it, but primarily so that we can get a sense for what the graph looks like. So if we rearrange this a little bit, we'll get x equals root y, or x squared equals y. X equals root y, or x squared equals y. Well, that is our classic parabola, y equals x squared. Perfect. 1, 2 goes to 4. There we are. And if we label that contour correctly, all the points on that graph have a z value or a height of 0. All right, that wasn't too bad. And we expect to see a theme when we do this again with different z values, or at least some similarities. So what we're doing is subbing in z equals 2 and getting the restriction or the relationship between x and y at that point. And that's going to give us, let's bring the y over and the 2 on the other side, root y equals x minus 2, or y equals x minus 2 squared. Now here we have to be a little bit careful. This is a parabola shifted to the right by 2, and so the temptation would be to draw this graph here, and then to continue on this side. However, there's a red flag immediately apparent. If we say all the points on this graph are at height 2, then this point here would be at both height 0 and height 2 at the same time. That seems a little improbable for a surface. So where did that issue creep in? If we go back to the original equation, we notice that this has to be a positive quantity. Square root of y has to be positive, but we're already working with that. But the square root of y, by default, is the positive version of that square root. And so we have a positive number equals x minus 2. That means x has to be bigger than 2 if this is going to work out. So bigger than or equal to would be okay. And so we're only talking about this branch of that function, all the way down to x equals 2. And that makes more sense. We can imagine a surface that's at height 0 along here, height 1, height 2, height 3, and so on. Just be careful. You cannot have contours that cross at different heights when you have a function of x and y. There should only be one z value for each point. And that's going to give us -1 equals x minus root y. And similar to these ones, we bring the root y over, and then we get x plus 1. Here we're not going to have too many issues with sign. X plus 1 squared, that's the same parabola shifted left. So we'll go through 1, 1, or 0, 1 rather, and up like so. And it has a z value of -1. And those are our contours. Next up, we're asked to evaluate the gradient. And again, we just remember the definition of the gradient. The gradient of a function, here we're calling it h, is the package of the x derivative and the, keep the letters the same, h partial derivative with respect to y. So we calculate those based on the original function, x minus root y. Let's actually rewrite this for a second. H of xy is equal to x minus y to the 1/2 is a much safer way to write this if we're differentiating. And so our x derivative is going to be 1, and our y partial derivative is going to be -1/2 y to the -1/2. That means that our gradient of h at the point 3, 1 is going to be equal to a package deal of the x derivative, and that's 1 no matter where, and then -1/2, and the y coordinate is 1, so we'll have times 1 to the -1/2. Fortunately, that's just 1. So 1 negative 1/2. Now that should work in concert with what we've computed earlier. If we take a look at our diagram, at the point 3, 1, we've just put a vector on that goes to the right and down like so. And that's a pretty reasonable approximation of what we expect for contours, which is that it's pointing in the direction uphill. Notice the z values are getting higher in this direction, and also perpendicular to the contour. So 2 checks on that. Next up, we're computing the directional derivative at 3, 1 in the direction of negative 4, 3. So what we're asking is, how steep is this surface if we were to go in roughly this direction on the surface? To begin, we need a unit vector in the direction of that negative 4, 3 vector. And to get that, we take our negative 4, 3, and we divide it by the length of negative 4, 3. And that's negative 4, 3 over 4 squared plus 3 squared square rooted. And that gives us 16 minus 25, 5. So 1/5 of negative 4, 3. That is going to be the unit vector in the direction of negative 4, whatever here, negative 4, 3. So that direction there is now u. And now we've scaled it so it's only length 1. What we're actually computing then based on that is the directional derivative of this surface at the point 3, 1 in the direction of u, and that is simply the gradient of h dotted with our u vector. We already found our gradient in the last question. We then take a dot product of that with the 1/5 negative 4, 3. That's going to give us 1/5 of 1 dotted with negative 4, plus negative 1/3 times 3. And that's going to equal 1 plus negative 4. That's negative 3/5. Last but not least, without calculation, identify the xy point where the global maximum of h occurs on the domain. A couple of different arguments here. If we look at the z values, those are our contours and these are the heights of the surface. It's clear that going in this direction is going to be the best. If we're trying to maximize our function, we can follow the gradient and try to follow it as close as we can. We're going to end up in the end at this corner at the point 4, 0. And a couple of explanations are following the gradient uphill within the bounds that we have here. And the bounds are confines. Another argument that would be just as effective is looking at the formula. If x minus root y is our formula, then if we want to maximize h, then what we're going to try to do is increase x as far as we can. That'll make it big. If we make y big, that's a problem because we're subtracting it, and we want to put y close to 0. And in fact, we're allowed to do that exactly at the point 4, 0. That'll maximize the value of h here. And that is section 7 for the 2017 exam.